Good morning, students. We are continuing with the organometallic chemistry, lesson 4. Let us today look at the transitional metal complex with the carbon monoxide, or you can call it metallic carbonyls. What are pi acid ligands and pi acid complex? Pi acid ligands are ligands such as carbon monoxide, nitrogen monoxide, you can name them, which have filled orbitals or donor orbitals, and as well as acceptor orbitals or the empty pi orbitals. These ligands combine with the transitional metals in a low oxidation state to form the pi acid complexes. Therefore, pi acid complexes are complexes of transitional metals in a low oxidation state with the pi acid ligands. These complexes have ligand metal sigma bonds as well as metal ligand pi bonds. Examples are the metallic carbonyls. Now, what are metallic carbonyls? These are compounds formed by the combination of carbon monoxide molecules with the transitional metal atoms in a low oxidation state. And in these compounds, carbon monoxide acts as a neutral ligand. Why do you think metals in metallic carbonyls are in low oxidation state? This is because of the fact that there are higher electron density or electronic charge on metals or on metal atoms in its low oxidation state than in the higher oxidation state. And since the metals are electropositive in nature, they could feel more comfortable if the excess electrons are transferred to the vacant pi orbitals of the carbon monoxide, resulting into the formation of the metal carbon monoxide pi bond. Classification of metallic carbonyls. They are mainly classified into two. We have classification based on the number of metallic atoms present in the carbonyl, and also classified based on the structure of the metallic carbonyl. So classified based on the number of metal atoms, they are also under two types. We have the mononuclear or the monomeric carbonyls. These ones contains only one metallic atom. An example is the nickel tetracarbonyl, the iron pentacarbonyl, and others. The polynuclear carbonyl, these molecules of carbonyl contains two or more metallic atoms. An example is the dicobalt octacarbonyl, the manganese decacarbonyls, and others. The polynuclear carbonyl may be of homonuclear, where we have only one type of metal in the carbonyl. An example is the dicobalt octacarbonyl and others. Then the heteronuclear carbonyl, where we have two types of metals within the carbonyl, as seen in these examples. The second classification I said is based on the structure of the carbonyl. These are also of two types. We have the non-bridged carbonyls and the bridged carbonyls. Under non-bridged carbonyls, we have carbonyls which contain only terminal carbonyl groups. Example is the nickel tetracarbonyl, the iron pentacarbonyl, the osmium pentacarbonyl, and others. And also we have non-bridged carbonyls, which contain terminal carbonyls as well as metal-metal bond. Example is the cobalt dicobalt octacarbonyl in solution, the dimanganese decacarbonyls, and the others. The bridged carbonyl. These contain bridging carbonyl groups along with the terminal carbonyl and one metal-metal bond. Example is the dimanganese N carbonyl and also the dicobalt octacarbonyl in solid state. A point to note here is that the mononuclear carbonyl always have non-bridged structure, while the polynuclear carbonyl have the non-bridged structure or bridged structure, as these examples highlighted. General methods of preparation. The first one is by direct synthesis. Here, carbonyls of nickel tetracarbonyl and pentacarbonyl can be prepared by this method, whereby there is a direct combination of carbon monoxide with the finally divided metal at a suitable temperature and pressure. So nickel plus carbon monoxide at room temperature and 1 atmosphere results into the formation of the nickel tetracarbonyl. And the iron plus carbon monoxide at 200 degrees Celsius and 100 atmospheric pressure results into the formation of iron pentacarbonyl. Another method of preparation is by reduction of the metal compounds in the presence of carbon monoxide. By treating the transitional metal compounds, an example, the metal halides, in suspended or in suspension in organic solvent like tetrahydrofuran or ether or diethylene glycol, you can name them, with the carbon monoxide at a pressure of 200 to 300 atmosphere and the temperature at 300 degrees Celsius in the presence of a suitable reducing agent results into the formation of the metal carbonyl. Mainly, the substance used as a reducing agents are metals like sodium, aluminium, magnesium, and others. All compounds such as trialkyl aluminium or sodium benzophenone can be used. Chromium hexacarbonyl can be prepared from chromium chloride plus carbon monoxide using the trialkyl aluminium in ether, resulting into the formation of the chromium hexacarbonyl. Similarly, molybdenum hexacarbonyl can be prepared from molybdenum pentachloride plus carbon monoxide and using sodium as a reducing metal in dimethyl ether, resulting into the formation of the molybdenum hexacarbonyl. They can also be prepared from iron pentacarbonyl or from a carbonyl like iron pentacarbonyl. Since carbon monoxide ligand in iron pentacarbonyls are labile, iron pentacarbonyl can be used to form certain carbonyls. An example is the formation of molybdenum hexacarbonyl, where we react molybdenum hexachloride plus the iron pentacarbonyl at 100 degrees Celsius in ether, resulting into the formation of molybdenum hexacarbonyl. Similarly, tungsten hexacarbonyl can be prepared. When we reduce osminium tetroxide by excess carbon monoxide, we also at 25 degrees and 350 atmospheric pressure, we obtain the osminium octacarbonyl. Physical properties. With the exception of nickel tetracarbonyl, osminium pentacarbonyl and others, which are liquid at room temperature, all other carbonyls are crystalline solid. They melt or decompose at low temperatures. They dissolve in nonpolar solvents. They are all diamagnetic except vanadium hexacarbonyl. Vanadium hexacarbonyl is paramagnetic because of the presence of unpaired electrons. The metals in carbonyls are in zero oxidation state. So as an assignment, briefly discuss the chemical properties of metallic carbonyl. Let us look at a few examples of metallic carbonyl. And the first one is the dimanganese decacarbonyl. Preparation. Dimanganese decacarbonyl is obtained when manganese iodide is reduced at high pressure of carbon monoxide by magnesium in diethyl ether. So manganese plus copper iodide at 500 degrees Celsius results into the formation of manganese iodide plus copper. So when this product is reacted with magnesium in the presence of carbon monoxide at 210 atmospheric pressure and 25 degrees Celsius at 16 hours, dimanganese decacarbonyl is obtained. Dimanganese decacarbonyl can also be obtained by the reaction of manganese diacetate with the triethyl aluminium and carbon monoxide at a pressure of 210 atmospheric pressure at 100 degrees Celsius for 5 hours. The equation is given below. It can also be obtained by carboxylation of manganese chloride in the presence of benzophenone, like that of benzophenone of sodium at 165 degrees Celsius, resulting into the formation of dimanganese decacarbonyl. They can also be obtained by the carboxylation of methylcyclopentadienyl tricarbonyl in the presence of sodium at 50 atmospheric pressure of carbon monoxide and 125 degrees Celsius for 80 hours. So methylcyclopentadienyl manganese tricarbonyl plus sodium and carbon monoxide at 50 atmospheric pressure and 125 degrees Celsius for 5 hours results into the formation of dimanganese decacarbonyls. Properties. Dimanganese decacarbonyl is a golden yellow crystalline substance with a melting point of 15 degrees Celsius and sublimes in the vacuum, soluble in organic solvent, and slowly oxidized in air when in solution. Action with the halogens. They react with the halogens to form carbonyl halide. Example, as in the equation below, dimanganese decacarbonyl plus bromine, it results into the carbonyl halides. Similarly with also iodine, it gives the carbonyl halide. When acted with lithium and sodium, with lithium, the metal-metal bond is broken in the presence of tetrahydrofuran. And in sodium, in the presence of liquid ammonia, we form the ion, the carbonyl ion. Reduction. When dimanganism pentacarbonyl, when dimanganism decacarbonyl is reduced by hydrogen under 200 atmospheric pressure at 200 degrees Celsius, carbonyl hydride is formed. So the dimanganese decacarbonyl plus hydrogen at 200 atmospheric pressure and 200 degrees Celsius, it results into the carbonyl hydride. Diamagnetic nature. It is diamagnetic substance due to the presence of paired electron. The structure is as shown. This is a non-bridged structure. Watch out when you are drawing this structure. The 2 electrons are being donated direct to the carbon, and also 2 electrons are donated to the metal as shown in the structure. Another example of metallic carbonyl is the iron pentacarbonyl. Preparation is prepared by the action of carbon monoxide at 200 atmospheric pressure on iron heated to 200 degrees Celsius. So iron plus carbon monoxide heated to 200 degrees Celsius at 200 atmospheric pressure results into the formation of iron pentacarbonyl. It can also be prepared by the action of carbon monoxide at 200 atmospheric pressure and 200 degrees Celsius on iron iodide in the presence of copper, which acts as an acceptor for iodine. So in this reaction, carbonyl iodide is first formed, which will react with copper in the presence of carbon monoxide to form iron pentacarbonyl. So iron iodide plus carbon monoxide results into the formation of the carbonyl iodide, which later reacts with the carbon monoxide and copper to give rise to the formation of the iron pentacarbonyl and copper 1 iodide. Properties. Iron pentacarbonyl is a yellow liquid which is soluble in methyl alcohol, ether, and other solvent. Action with the ultraviolet light. When irradiated, it results into the formation of diiron N-carbonyl and carbon monoxide. It decomposes at 250 degrees to give pure iron and carbon monoxide. On hydrolysis with the acid, it results into the formation of iron sulfate, carbon monoxide, and hydrogen. When heated with the aqueous sodium hydroxide and acidified, it results into the formation of the carboxylate ion. When reacted with the ammonia, it gives the carbonic acid and other products as shown in the equation. Reaction with the halogens. It reacts with the halogens in non-aqueous solvent to form the stable tetracarbonyl chloride. So iron pentacarbonyl plus the halogen, it gives rise to the tetracarbonyl halide. When it is burnt in the air, it gives a finely divided ferric oxide, which is used as a pigment and a polishing agent. And the structure, we have 2 structures, possible geometrical molecules. We have the trigonal biopyramidal structure, which looks like this, and also the square pyramidal structure. So next time, we are going to look at more examples. of metallic carbonyls.